Before we begin our discussion on error, I'd like to take a look at a sum. So that's not an integral, that's a sum. Suppose we have 1 minus a half plus a fourth minus an eighth plus a 16th, so on and so forth. So the sum is equal to that. You would probably recognize that as geometric. But suppose we said the sum was approximately 1 minus a half plus a fourth. Okay? So that would be accurate to some degree, but you would see that there is an error in this approximation. The error would be negative 1/8 plus a 16th minus a 32nd, and that pattern would continue for the error in approximating that. If we look at a second sum, and let's let this sum be 1 minus a fourth plus 1 over 192 minus 1 over 46,080. This sum is not geometric, but the same concept applies. If we approximated the sum, of the first three terms, then there would also be some error. And the error would be what's left over, 1 over 46,880 plus ... whatever those terms would add up to be. Okay, so that gives you a sense of where we're going in this unit. We're looking at an approximation plus an error. Now in some cases you can actually calculate the error, such as this case here. We can calculate the error because the error is a geometric series. So the error here would be exactly, first term would be 1/8, 1 minus the common ratio, and the common ratio is negative a half, which equals, that's going to equal negative 1. So the error is negative 1/12 if we approximate using the first three terms. The error here, we can't find the exact error, which leads to the unit, which is approximating error, and that's why we call this error analysis. So now if you pull out your notes, we're going to fill in the first part of it and then continue through to take some notes on the examples. So let's begin. We begin by saying that f of x, some power series, is approximately equal to a polynomial of order n. And we could also say then that f of x is equal to the polynomial of order n plus some error, as shown in the illustration before. So we say that this error, another name for it, is remainder. So f of x is the polynomial plus some remainder. You will notice, please, that this n says that the remainder following this polynomial of order n. So we conclude by saying that the error in magnitude is equal to this remainder, which is then in turn equal to f of x minus the polynomial. And then, as the illustration before showed, we most of the time deal with the function at some value a, so we're not looking at a power series, and that's approximately Pn of a. And the same sort of pattern applies here, that f of a is the polynomial at a plus the error or the remainder at a. And once again, we talk about error in magnitude, which is equal to Rn at some value a, which then equals f of a minus the polynomial at a. Okay, we are ready to look at some examples in the notes. Theorem E1 will be the focus of this first video. In Theorem E1, you have to listen to it carefully. You can also read it on the front page of the notes. It says that if a series is strictly alternating and decreasing in absolute value to 0, if the terms of the series are strictly alternating and decreasing in absolute value to 0, then the error, the entire error, this is awesome, the entire error is less than or equal to the first omitted non-zero term. Remarkable. So, in the example before, where we had 1 minus a half plus a fourth minus an eighth plus dot dot dot, if we said that we're going to look at this here, according to E1, the theorem, then the error in magnitude is less than or equal to the first omitted term. So that would be 1/8. So the entire error is going to be less than or equal to 1/8. In fact, we found that the error was equal to, in magnitude, 1/12. But again, they're not all geometric, so we don't always know what the error is. So, without further ado, example number 1. In example number 1, it says use the first two non-zero terms of a Maclaurin series to approximate the sine of 0.1. So we start off this discussion with recalling a power series for the sine of x. So we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot. So then a series for the sine of 0.1 would be the same thing, except we would substitute 0.1 in for each term of the series. 0.1 to the 5th over 5 factorial minus 0.1 to the 7th over 7 factorial dot dot dot, and that's factorial. So this says use the first two terms. So the sine of 0.1 is approximately equal to 0.1 minus 0.1 to the power of 3 over 3 factorial. And then we're going to say with error and magnitude less than or equal to the first omitted term. So the error is going to be less than or equal to 0.1 to the 5th over 5 factorial. Now you could do some arithmetic here. 1/10 to the power of 5, that's going to have 5 zeros. 5 factorial is going to be 120. So if we put that together, it's going to be 6 zeros following the 12. So that's 12, 0, 0, 0, 0, 0, 0. That is a very small error. We say that the entire error is smaller than that fraction. And that kind of makes sense because we're picking a value 0.1, which is very close to the center 0. Now, had we picked a value of, let's say, sine of 7, well then 7 to the 5th over 5 factorial is going to be very large, and that's not telling us much because the error can be very, very, very large. Anyway, we say the statement that the error is less than or equal to the first omitted term because we say this is true because the series the series for the sine of 0.1 is strictly alternating and decreasing in absolute value to 0. With that quality, we are able to bound the error by the first omitted term. Let's take a look at example 2. In example 2, it says we are to approximate the integral of the sine of x squared from 0 to 1, accurate to 4 decimal places. Okay, So we have committed to memory a power series for the sine of x, so we can quickly manipulate and convert that, or substitute and convert that into the following series: x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial plus dot dot dot, and of course with respect to x. So now we're going to integrate each term, term by term by term. So this is going to be x cubed over 3 minus, this is going to be x to the 7th over 7 times 3 factorial plus x to the 11th over 11 times 5 factorial minus x to the 15th over 15 times 7 factorial, so on and so forth. Okay, so we have to take that using the fundamental theorem of calculus part 2 from 0 to 1. So when I plug that in, I get a third minus 1 over 42 plus 1 over 1,320 minus 1 over 75,600 plus dot dot dot. The 0 contributes nothing to the series. So we say then that the integral from 0 to 1 of the sine of x squared dx is approximately 1/3 minus 1 over 42 plus 1 over 1,320. And the error, so now with error and magnitude less than or equal to the first omitted term, 1 over 75,600. And we have to ask ourselves, how did we know to stop here? Well, you can see this is clearly 0.3 repeating. This decimal here, the 1 over 42, in magnitude is 0.0238, which clearly contributes to the 4th decimal place. The next decimal approximation is 0.00076, and this still contributes to the 4th decimal place. So it's not until you get to this term, which is something crazy, 0.000013, and that will not contribute to the 4th decimal place, because the error at its best, the total error at best, is equal to this, which will not contribute to the 4th decimal place. So that's why we stop with these 3 terms, because they all contribute, and then the error is estimated to be less than that big fraction. Again, and this is true, so we write this is true because the series for the integral from 0 to 1 of sine of x squared dx is strictly alternating and decreasing in absolute value to 0. That's our E1 theorem. Example 3 will be on the next video. I encourage you to try example 3. Example 3 is an AP exam from the 1990s. Please try it, do the best you can, and then start the second video where I will go over example 3. Examples 4 and 5 are homework assignments and will be gone over in class.